warm summer day has a pressure of 100,000 pascals and a temperature of 300 Kelvin. There follow a series of questions regarding the ideal gas law. Part A asks us to find the number of moles per cubic meter of any ideal gas under these conditions. Well, the ideal gas law tells us that pressure times volume is equal to number of moles times the ideal gas constant times the temperature T. Although in many of the physical laws that we deal with, Celsius units are okay, in this one they're not. In general, the laws that have a delta T, a difference in temperature between 2 points, are amenable to both Celsius and Kelvin because delta T is the same amount in both Celsius and Kelvin. Here we have a T that stands alone, and when the T stands alone, you must use Kelvin in order to get the proper units. Since we've been asked for moles per cubic meter, we recognize that moles is the number N, and cubic meter is the volume V, so we can solve the ideal gas law to find that moles per cubic meter is simply equal to pressure divided by the ideal gas constant times T. In our case, we're using MKS units for the pressure of 100,000 pascals, and for the temperature we'll be using 300 Kelvin. The version of the constant R that we use is 8.314. That's the one in joules per mole Kelvin and will lead us to the result in the units that we desire. So what we find is that the number of moles per cubic meter of any ideal gas under these conditions is 40.1 moles per cubic meter. In part B of this problem, we've been asked not to find the number of moles per cubic meter, but instead to find the number of kilograms per cubic meter of nitrogen gas under these same conditions. What we recognize, simply examining the units, is that kilogram per cubic meter can be related to moles per cubic meter by a single constant. That constant would have the units of kilograms per mole, and we recognize that constant as being the molecular weight, so that the density of any material will be equal to the moles per volume times the molecular weight, for which we use the symbol capital M. Nitrogen is an atom with 7 protons and 7 neutrons for a total mass of 14, and since the N2 molecule has 2 of these nitrogens, it has a total mass of 28 grams per mole. However, in this course we use kilograms per mole, and so what we'll be doing is taking the N over V from the previous step and multiplying it by 0.028 kilograms per mole, which is the same quantity as 28 grams per mole. This leads us to the density of nitrogen gas as being 1.12 kilograms per cubic meter. Nitrogen, under these conditions, is a very good approximation for the air that surrounds us, since the air is made of 70% nitrogen. If you look up the typical density of air, you're going to find a number that's very close to this one. Let's move on to Part C. The calculation in Part C is extremely similar. We're asked to find the kilogram per cubic meter, not of nitrogen, but instead of helium, which is a monatomic gas under these same conditions. And we recognize from the previous problem that the density will be equal to the moles per unit volume times the molecular weight. Although the moles per unit volume of any ideal gas under these conditions is 40.1 moles per cubic meter, this time, when we apply the molecular weight, we recognize that helium has 2 protons and 2 neutrons for a total molecular weight of 4 grams per mole, or 0.004 kilograms per mole. This leads us to a helium density of 0.16 kilograms per cubic meter. Comparing this result to the previous step, we find that the density of helium gas under the same pressure and temperature conditions as nitrogen is much, much less. This is what makes helium buoyant within the air. In part D, we're asked to determine the net force on a 1.5 cubic meter helium balloon in air. And we're to use the calculation in part B of the density of nitrogen as a reasonable approximation for air. Well, the first step in every force problem is to draw a free body diagram, and this dot will represent our helium balloon. The first force we think of in most free body diagrams is the force of gravity. This one tends to fool students in this problem because a lot of students will claim that gravity pushes upward on helium. Nothing could be further from the truth. Gravity pushes downward on all things, and therefore the force of gravity on the helium will be equal to the mass of the helium times g. Since the helium is a fluid or a continuous medium, we don't like to use mass as our determining factor for how much helium is there. Instead, we would like to use the density of the helium, which we'll need to multiply by the volume times g, and this will be the gravitational force downward. We all recognize that when you release a helium balloon in air, it doesn't go to the ground, instead it goes up. The reason is that the buoyant force acting on the helium, because it is immersed in air, is actually greater than the gravitational force pushing downward. And as always for the buoyant force, the strength of the buoyant force is the density of the fluid in which you are floating. The fluid will be taken to be the nitrogen gas times the volume times g. This is a one-dimensional free body diagram, and we know that the helium balloon will accelerate upward, and so we will select up as the plus direction. In this case, the net force is the sum of all forces and will be equal to the density of the nitrogen times the volume displaced, which is the volume of the balloon, times g, minus the density of helium times the same two factors. Plugging in the numbers from the previous steps will give us the answer for the net force acting on the helium balloon. The result is 14 newtons upward. It's worthwhile to note why the helium balloon goes upward. The helium balloon goes upward because gravity pulls the nitrogen gas of the air downward to take its place. An interesting experiment for you to try is to tie a helium balloon by a string in your car. When you step on the gas, the helium balloon will go to the dashboard. When you step on the brake, the helium balloon will head towards the back seat. Why? Because when you hit the gas, the nitrogen heads towards the back seat, pushing the helium towards the dashboard. When you hit the brake, the nitrogen heads towards the windshield, pushing the helium balloon towards the back seat. This is why, in the presence of gravity, when the nitrogen goes down, the helium balloon goes up. Finally, we've been asked to determine the root mean square velocity of the helium atoms. In order to do this, we need to recognize the relationship that defines temperature in terms of earlier quantities taught in this class. What we've learned is that the average translational kinetic energy per molecule of any ideal gas is proportional to the temperature with a proportionality constant 3/2 times the Boltzmann constant times the temperature T. The Boltzmann constant has a similar role in physics to the ideal gas constant R. Both of these are to account for screwy units in the equations that we're choosing to use. The ideal gas constant is in joules per mole Kelvin because we should use joules for all energy quantities, but in the ideal gas constant we came up with screwy units called both moles and kelvins that kind of ruined it. In this case, an average kinetic energy will be in joules, but our temperatures are still in Kelvin. And so the Boltzmann constant comes into the game having a value of 1.38 times 10 to the minus 23 joules per Kelvin. Since we know the formula for translational kinetic energy is 1/2 mv squared, we can pull the 1/2 m out of the average, so that we'll have 1/2 m times the average value of the velocity squared of our helium atoms is equal to our 3/2 k times t, so that the square root of the average of the velocity squared of these helium atoms is the square root of 3 times the Boltzmann constant times the temperature in Kelvin divided by the mass of a single molecule. Often this formula is looked upon to have inconvenient units. What we can do underneath the square root is multiply by a factor of Avogadro's number, both numerator and denominator. When we take the Boltzmann constant times Avogadro's number, we'll be asking for the number of joules per mole Kelvin. Well, that is, our friend, the ideal gas constant in joules per mole Kelvin. And when we multiply by Avogadro's number in the denominator, we'll have the number of kilograms per mole instead of per molecule, and that is the molecular weight. Either one of these formulas will produce exactly the right answer. Since we recognize that the left-hand side of this equation is equal to the square root of the mean of the velocity squared, this quantity is the RMS, or root mean square, value of the velocity. The average velocity of the gas molecules is 0, because half go to the left and half go to the right, giving an average velocity of 0 unless there happens to be wind. However, the root mean square velocity is not 0, and it is equal to the value 1368 meter per second.